Okay, so here we talk about the energy stored in an electric field. Okay, so this electric field is of course generated by the capacitor, by the capacitor. So yeah, so for the easiest case, if we have parallel plate capacitor, there will be E field into it, and we also assume the E field is uniformly distributed. So as much as there are some energy stored there, so we will also consider there are some energy stored in this electric field, or actually we need to use some energy to generate this E field, depends on how you look at it. Okay, so here is set electric potential energy. Okay, so yeah, this U is the electric potential energy of a charged capacitor. Is this one, U equals the integration of dU, and of course U equals QV. Okay, so here we try to separate a distribution of charge into many small parts. Each part is dQ prime, and here the idea is like originally all the charge are placed infinitely far away, so in this system there isn't any potential energy. So initially the potential energy is zero. So we try to put this dQ prime for each part. We put it into this system one by one. So we have this integration. So V times dQ prime, and then we have a zero integrate from 0 to Q. So yeah, so for capacitor, we have Q equals CV, or V equals Q prime over C. So in that case, C is a constant. We can put it out, and then we just integrate this Q prime dQ. So it is actually Q prime square. If you divide from 0 to Q, which become Q square, and then over 2, Q square over 2, and then yeah, and then all over C. So it's like this. So Q square over C. And actually, if you just make use of Q equals CV, and then you plug in this one into here, so here we have a C square V square, so it becomes a CV whole square over 2C. So one of the C cancel, so it becomes U equals 1/2 CV square. Actually, I usually use this one, okay, rather than Q square over C. From a circuit point of view, we seldom consider the charge, okay, so we will consider the current or the voltage or something like that. So U equals 1/2 CV square is can be used more frequently. Okay, so here it's also said in this highlight is that the potential energy of a charged capacitor may be viewed as being stored in the electric field between the plate. Okay, you store the energy in the E field, energy in the E field, or from another point of view, just as what I said, you can consider you use some energy to generate the E field between the capacitor, because you need to do some work to put the energy close together so that they have some potential energy in between. Okay, below one is a more physics equation. I seldom use it in our engineering problem, but later in chapter 33, when we talk about the EM wave, electromagnetic wave, 电磁波的时候, then we will make use of it to show that the energy stored in the E field and also stored in the B field in an EM wave. Okay, these two parts will be equal. These two, I mean, is the energy density. The energy density stored in the EM wave. Okay, so we have a part for the E field. We have also the energy density for the B field. Okay, but here U equals 1/2 epsilon naught E square. So this is the This is the density. This is the density, energy density. Actually, I will not try to prove this one. I will not try to prove this one, but actually we can try to verify it with a case for the parallel plate capacitor. So for the parallel plate capacitor, we have a U equals the total energy divided by the volume. Okay, so suppose we have the, okay, so this is the parallel plate capacitor, parallel plate capacitor. So we have U equals A over D, because if you have a parallel plate capacitor, the area of a plate is A, and then the distance is D. So the volume at for this part will be A times D, the surface area times the distance between them. So this is the volume. Okay, so this is the volume equals A times D. Okay, so we can try to make some substitution. So we have A over D, put it in the front, and then here U equals 1/2 CV squared. So we put it here, 1/2 CV squared is U. So and actually for this parallel plate capacitor, C equals epsilon naught A over D, if you still remember. Okay, so here we have put the 2 in the front, so we have 2AD in the front in the denominator, and then we have C will be this epsilon naught A over D, epsilon naught A over D, and then we have V squared. Okay, so we just substitute this C by this part. Okay, so the remaining stuff will be like we can do some cancellation. We cancel this A with this A. Okay, so the area doesn't matter, because it's like the energy density. So it shouldn't be it doesn't really relate to the cross section area. So finally, here we have D, we have also another D, so totally D squared, and then we try to group the square term together. So here we have a 1/2 epsilon naught, okay, for here is 1/2, here is epsilon naught. Okay, so here we have D squared and then V squared. So altogether it becomes V over D whole square. Something like this. So it's just some algebraic computation. 只是一些代数运算. Okay, so in that case, V over D. So suppose this place is a positive charge, and then this place we have some negative charge. So the potential difference is this place has a higher potential, this place has a lower potential, V. So V over D will be the magnitude, the E here. Okay, E. So we have E equals V over D for uniform charge. Okay, if you don't remember, it is something like this. V equals negative integration of E dot ds. Okay, so if E is uniform, then V equals E times this distance. Okay, we call it D here. So V over D equals E. Okay, so it turns out to be 1/2 epsilon naught E squared. Okay, so this is actually this stuff. Okay, so we have used the parallel plate capacitor to verify this equation is correct. Okay, we don't try to generally prove it. Okay, so so actually this for this equation, even though we derive it here, we can seldom use it. Okay, it's just used for the chapter 32. Okay, to explain the characteristic of the EM wave. Okay, so here we have a sample problem. So it said an isolated conductor sphere whose radius r is this length and has a charge q. How much potential energy is stored in the electric field of this charge conductor? Okay, so actually we have a sphere. Okay, isolated sphere. Okay, so you can imagine, okay, it will generate an E field, so E equals K times Q over R squared. E equals K over K times Q over R squared. Okay, at the surface, yeah, because actually, yeah, so all the charge will be distributed on the surface, and inside the sphere there won't be any E field, so the E field is generated, actually starting from the surface to the outside part. Okay, so in that case, U equals 1/2 epsilon naught E squared. So it actually asks you the energy density at the surface. So we only consider R equals capital R part. Okay, so the surface is here. So yeah, this is R. Okay, so this is like a surface density, energy surface density. Okay, so in that case, we have we have so we have a 1/2 epsilon naught, and then we have a K. So let me try to write it out as 1 over 4 pi epsilon naught, and then 1 over 4 pi epsilon naught. Okay, because here we also have an epsilon naught, so I just try to write the whole thing here. And then we have a Q, and then over capital R square. And then this whole thing we have a square, because here we have E square rather than E. So this whole thing is E, and then we take the square of this whole thing and then multiply by epsilon naught over 2. So altogether we have a 1/2 epsilon naught, and then we have a 16 pi square epsilon naught square, and then R to the 4th power, and then here we have Q square on the top, like this. So altogether we have a 32 pi square epsilon naught. Okay, one of it is cancelled. One of the epsilon naught is cancelled with this one, and so we have R to the 4th power here, and then on the top we have Q square. So in this case we can just substitute the numbers. So Q is 1.25 times 10 to negative 9. Okay, so if you haven't memorized the scientific prefix, so just take this time to do so. 就是我说过，就是考试的时候你不能够问这些什么 N 啊 P 啊 F 啊那些是什么。你问一个单字是什么意思是可以举手发问的，但是你不能够问那些什么 N 是多少啊什么之类的。Okay, so we have a 32 pi square, and then times epsilon naught is 8.85 times 10 to negative 12, and then times 0.0685 to the 4th power. So this is 25.4 times 10 to negative 6. Okay, so this is the energy density at the surface. So it's the surface density. So the SI unit for the energy is joule per, and then meter square. I think meter square. Okay, or you can actually write it as 25.4 microjoule per meter square. So both are okay. Okay, so this part we will try to talk about something called the dielectric. Dielectric， 中文叫做电介子。Okay, so it is an interesting material. Actually, I don't know what it is in the practical world. So yeah, but actually the dielectric is something like it has some different property compared to the air or compared to the vacuum. Okay, compared to the air or compared to the vacuum. Okay, so maybe there's some solid. Okay, so actually it has some interesting property. So it said if the space between the plate of a capacitor is completely filled by dielectric material, the capacitance C in vacuum or effectively in air is multiplied by the material dielectric constant. Okay, so and then this dielectric constant we call it kappa, not K. Okay, it is Greek letter. 这是一个希腊字母，它是 kappa， 它是 kappa. Okay, and this kappa is always greater than 1. Okay, greater than or equal to 1. For air, for vacuum, we will consider this kappa is 1, and for other material, it must be greater than 1. It must be greater than 1. 因为如果你能够找到一个小于1 kappa 小于1的东西的话，就代表说你能够超越光速了就代表说你能够超越光速，所以目前的话还不行。Okay, so here. 就是这个说了一个很奇怪的东西，他突然间就告诉你说，如果你把一个电容，本来电容两个平衡板中间是空气，空气的话跟真空的电的特性是一样的，空气跟真空是一样的或者是非常接近的，我们可以忽略的。那现在他说，如果我们在平衡板中间放一个 dielectric 就是像一个三文治那样，就是你放个夹心进去，这个电介质的话，它就会有一个kappa， 它有一个 kappa， 然后它会让这个电容值变大，它会让电容值变大。OK， 所以我们看看so let's take a look at these two experiment. These two experiment. Well, before it, we have a highlight. So this is that in a region completely filled by dielectric material or dielectric constant kappa, or electrostatic equation containing the permittivity constant epsilon naught are to be modified by replacing epsilon naught with kappa epsilon naught. So 所以这个意思是很简单它的规律就是说，本来如果没有电介质的话前面有很多公式，它会有 epsilon naught 这个常数，这个 permittivity constant 的出现。那如果我们要处理一些有电介质的时候而这个电介质是 kappa 的话，我们只需要把这个 epsilon naught 所在的公式换成 kappa epsilon naught， 它就会正确了，它就是自动正确，我们不用再重复再推导什么的了就直接换就好了。直接换 Okay, so here let's take a look at these two experiments. So the first one is that if potential difference between the plates of a capacitor is maintained. Okay, so the potential difference is maintained as by the presence of the battery B. The effect of dielectric is to increase the charge of the plate. Okay, so here we first take a look at the left hand side. So here this is the circuit. So first we have this capacitor and then we have a battery here. So let's say the potential difference is V for this battery, and so this capacitor also have this potential difference here. And here we just remain the potential difference to be V at this case, and in between we try to put in a dielectric between the capacitor. In that case we will see that the charge stored here become larger. So here V doesn't change, but Q increase. So originally Q equals CV, and then V is a constant. Means, yeah, this battery doesn't change. So the potential difference here doesn't change either. So in that case, we know Q equals CV, or we can try to make it like C equals Q over V. Okay, so here V doesn't change and Q increase. So in that case, C increase. Okay, so which means C increase. So here we find that C increase for this case. Okay, and then for the second case is that if the charge on the capacitor plate is maintained. Okay, as in this case, by isolating the capacitor of the effect of the dielectric is to reduce the potential difference between the plate. Okay, so here it's like it's starting like we first have a capacitor and then we try to charge it with a battery. We try to charge it with a battery with a potential difference V, and then there will be some positive charge on the top plate and then some negative charge on the bottom plate. So it is a positive Q and negative Q here. The potential difference is plus and minus V. Or is potential difference is V, I should say. So in that case, we try to disconnect this battery. So after disconnecting the battery, the Q doesn't change because any charge cannot go in or going out. And then we try to connect a voltmeter. Okay, so voltmeter 就是一个电压的表电压表，去测它的电压怎么变化。一开始的话应该是没有变化的，因为它 C 没有变 ，C 还是原来的 C， 所以这个 V 还是维持着这个 V 还是维持着这个部分。那 Okay, so in that case, we try to also plug in this dielectric between the capacitor. So in such a way, the Q doesn't change either. And then the C. Okay, we don't know the C, but as we try to measure this voltage or potential difference. Okay, you see on the left side are the volt. Okay, so this one has a higher potential difference, and this one the potential difference will decrease. So we will say the potential difference now becomes V prime, which is smaller than V. V prime is smaller than V. Okay, so here, what is the C prime here? C prime will also be Q over V prime. Okay, so or maybe you can just consider it originally is C over Q, C equals Q over V, and now Q doesn't change, but V decrease to become smaller V prime. So in that case, C is decrease. Oh, sorry, C is increased. Yeah, because the denominator decreased, so this C should increase. So for both cases, we try two different settings, and finally it turns out that if we try to put in some dielectric inside the capacitor to replacing the air, okay, the capacitor. The capacitance becomes larger. Okay, so this is the conclusion for these two simple setup. So here we try to talk about the capacitor with a dielectric in a more physics point of view or an atomic view， 就是从一个很原子或者是分子的角度去看这个事情这个是OK. So inside the dielectric material, okay, there will be quite a lot of this kind of polar dielectric. 就是有一些像一些 dipole 啊，或者是化学里面有一些什么有极性的分子之类的东西啊 ，dipole 有一些 dipole 啊，所以它就是每一个都会看起来像一个正电荷一个负电荷在一个很短的距离 d， 然后一个正 Q 一个负 Q， 每一个都是这样它只是用图蓝色代表正的，橘色代表是这个负的，然后这里就会有一个dipole moment dipole moment P equals QD P equals QD， 就每一个都这样 ，OK。So yeah, so if we don't have if we don't have any E field, don't have any external E field outside, so all these dipole will randomly point to different direction, and then the E field, of course, the dipole will generate some E field, but if all these dipoles points to different direction or randomly points to different directions, then all this E field will somehow cancelling each other, so that it won't generate any E field. But if we try to apply some external E field, then there will be something interesting. Okay, so just like here. Okay, so the first case is here. So this one is the first case. Okay, originally initial E field inside the polar dielectric slab is 0. Okay, so we don't provide any external E field. Okay, E external is also 0. Okay, in that case, this dielectric material won't generate any E field inside the material itself. Okay, so for the second case, okay, this part and this part are two parallel plates, and we have some positive and negative charge. So this part you can consider is a big capacitor. Okay, it's a big capacitor. Just as what we did, okay, before plug in the dielectric, and now we try to plug in this dielectric. So just as what we did here, okay, we try to plug in the dielectric material inside the capacitor, but here we just only try to see what it's really inside. Okay, so in that case, there's some interesting property here. Okay, so for this green dot, it is just like here. Okay, so all the dipole are just point to different directions randomly. Okay, but here, if we apply some E field, all these dipole will align to the same direction. Okay, actually, all the positive side will point to the right side. Okay, here is a external E field. It's generated by this here, this capacitor. So there will be a E field. This E0. Actually, this is E0 is the external. This is the external E field. Okay, external E field. So if here, okay, this capacitor will generate an external E field for this material, like E0, actually pointing to the right side. So in that case, all this dipole, the positive side will go to the right side, and the negative side will point to the left side. Okay, so all the dipole will align. Okay. 就是有点类似是说，就是比如说在一个教室里面如果现在不是上课的话，那可能同学的话就不一定是全部都朝着这个方向，可能是你可能就是朝着后面跟朋友聊天，或者是你在随机的移动，可能出去上个厕所倒个水或者是什么，就大家都很随意的朝着不同方向。但是现在的话 ，external E view 就好像是现在在上课，就好像拿个电场作用在那个dielectric material 上面这样现在在上课，那所以大家的话正常的话都会朝着同一个方向，就类似是这个意思。 Okay, so in that case, of course, this one is the E field, the external E field. This one is generated by the capacitor. Generated by the capacitor, and actually here we will have some E prime. E prime is actually generated by the dielectric. Generated by the dielectric. Why? Because all these dipoles align to the same direction. So in that case, we will have an E field. We will have many small E field. Many small E field pointing to the left side, and all these small E field adds up. So finally, all these E double prime adds up to this E prime. Okay, so this E prime will point to the opposite direction of the external E field. So this is the total. This is the total E field. Total E field inside. The total E field inside the inside. This is the total E field inside, which is this one. Okay, so it turns out that this E field will be smaller than the original external E field. Okay, so this is the property for the dielectric material. Okay, so here we try to take a look at this slide. So it says the dielectrics and Gauss law. So inserting a dielectric into a capacitor causes induced charge to appear on the faces of the dielectric and weaken the electric field between the plate. Okay, 所以这个它的意思是说因为所有这些 dipole 都这样的就是对齐了它对齐了。那所以的话，就相当于有一个比较弱的正电荷有一个弱的正电荷，跟一个也很弱的负电荷，一个弱的负电荷，这样产生。但这个很弱，其实中间的话，它很多会抵消掉，但是只有很小的一排，很轻微的有一个正跟负跟外面的这个反方向所以的话。它看起来像一个 induced 的一个很弱的电荷，就是generate induced charge to appear on the face of the dielectric and weakens the electric field， 就是它会减弱，会抵消掉外部电场的一部分 between the plates. The induced charge is less than the free charge on the plates. So when the dielectric is present, a Gauss law may be generalized to this. Okay, originally it is the Gauss law is like something like this: epsilon naught integration of E dot dA and then equals Q enclosed. Some pages before tells you that if we have a dielectric, so we try to replace this epsilon naught as kappa epsilon naught. So maybe you will say, whether is it like epsilon naught kappa integration of E dot dA? But here it tries to put this thing inside. Put this thing inside means maybe in this region we have several different types of dielectric, so they have different kappa. So it just tells you that for this integration you just consider different kappa. You just consider different kappa, so that it just try to make it more general 就是让这个式子更推广一些，就是如果只有一种那个电介质的话，你 kappa 放里面放外面是一样的，但是有时候有些情况可能它那个平衡板中间你硬要放几种不同的电介质，它们有不同的 kappa， 那就是提醒你说不同的区域有不同的 kappa， 那你就稍微注意，你积分的时候就要可能分开。 Okay, so yeah, so it would be something like this. Okay, so you just mentioned that originally we have a capacitor, inside we have some air, and here we try to plug in a dielectric, so it feels like there are some induced charge on the surface, but this induced charge is weaker than the capacitor outside. And actually, if you already consider this copper in the Gauss law, you don't need to consider this Q prime again. OK， 就是说它这里有提到这里有一个 Q prime 的，如果你的式子已经有这个 copper 在的话，你就不用管这个 Q prime 啊，你就不用管这个 dielectric 所产生的这个 induced charge 啊，因为他们所形容的是同一个事情。如果你两边都考虑的话，会重复。有其中一个例题是问这个 Q prime 是多少的，所以到时候的话，就那种情况是等于说，如果我没有考虑 Q prime 的时候，我这个式子是有 copper 的。那如果我这个式子是没有 copper 的时候，它应该会像Q 减去 Q prime， 这样才正确，那到时候就会可以用这两个去比较一下，去求出当我知道 copper 之后，我就可以知道这个 Q 跟 Q prime 的那个大概比例是多少，那从而知道这个 Q prime 是多少。到时候 selected problem 的时候可以去看一下有其中一题是跟这个有关。And then there's a log here, so it says the flux integrating now involve copper E, not just E. Okay, so the vector epsilon naught copper E is sometimes called electric displacement. Okay, 所以在某一些的那个文献里面，他们会有这个。或者是更高阶的电磁学的书，他们会引入这个 D 但是这本书里面后面其实一次都没有再出现过，所以其实只是告诉你一下，电磁学里面它还可以定义这个 D 就是说把这个 F copper E 全部都定义成一个 D。那高斯定律的话，它就可以写成。高斯定律它就可以写成 integration of dA， 然后等于 Q equals 它就少了前面那个常数，让它更简单的感觉。但我们就没有必要很去考究这个事情，因为后面也没有再出现。你记太多东西的话呢，就会把不懂的东西搞得更混。对，所以就让大家知道有这个东西就好。Okay, so wow, this one is quite long. Okay, so maybe let me